Hello, bonjour, konnichiwa, good dag. Welcome to the first tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. Our subject today will be the convergence of Markov chain Monte Carlo algorithms. And our main tool will be this stone, this pebble. Moving around the 3x3 pebble game, it will allow us to derive and illustrate a profound mathematical result that is of great practical importance. We will show that the convergence of Markov chain Monte Carlo algorithms is exponential. This means that a Markov chain Monte Carlo algorithm is characterized by a time scale, the convergence time tau. It is on this scale that we approach equilibrium, and that the pebble positions on the 3x3 pebble game become equally probable. After a few times tau, a Markov chain Monte Carlo algorithm is in equilibrium for all intents and purposes. In the same way that after a few nuclear half-lives, a radioactive compound has completely decayed. Let us now return to the 3x3 pebble game and understand its exponential convergence. On the 3x3 grid, we label the sites from 0 in the lower left corner to 8 in the upper right corner. The Markov chain Monte Carlo algorithm, as discussed in lecture 1, consists in moving the pebble with probability 1/4 to the right and to the left, up and down. When a move is not possible, it is rejected, and the pebble remains on the same position for the next iteration. In Python, this gives the following program. The list neighbor contains 9 lists with 4 sites each, corresponding to the moves to the right, up, to the left, and down. So here is the configuration at time 0 with the pebble on site 8. The function randint of 0 and 3 samples random numbers 0, 1, 2, and 3 with equal probability. If we choose 0, we'll try to move to the right, but this move is rejected. If we have randint equal to 1, we'll move up, but again this move will be rejected. If randint equal to 2, we'll move to the left, and if it is equal to 3, we'll move down. Before running this algorithm, let us ask a few questions. First question. If at time t equals to 0, the pebble is in the upper right corner on site 8, on which sites can it be at time t equals to 1? Of course, it can be on the sites 5, 7, and 8. In fact, the pebble will remain on site 8 with probability 1/2, and it will move to sites 5 and 7 with probability 1/4 each. Question 2. At what time does the probability to be at site 0 become finite? The answer is that it becomes finite at time t equals to 4. at t equals to 0, 1, 2, and 3, it is 0 because it takes at least 4 steps to connect the site 8 to the site 0. The probability to be at site 0 is non-zero for times t equals to 4 and larger. Now, final question in this sequence, question 3. What is the probability to be on site 0 at time t equals to 4, given that the pebble started on site 8 at t equals 0? Attention! The probability is a fraction, and it is not easy to find. The answer is that this probability is equal to 6 over 256, or 3 over 128. The denominator, 256, is equal to 4 to the power 4, because there are 4 moves, and at each move we have 4 possibilities. The numerator, 6, corresponds to the 6 ways of connecting site 8 to site 0 in 4 steps. From our Stone Age 3x3 pebble games, we now move on to a program capable of doing graphics. The red pebble that you see here starts on site 8, then moves on to neighboring sites, hops back, goes on, touches site 0, and so on, until after a long time all the positions become equally likely. Next in this tutorial, Michael will discuss this simulation without watching pebbles hopping around the 3x3 pebble game. But before moving on, please take a moment to download, run, and modify the programs we just discussed. On the Coursera website, you will find the program pebblebasic.py that we just discussed. You will also see the pebblebasic movie.py that produces the nice graphics output. Okay? It's your turn.
Now let us modify a bit the simulation program for the 3x3 pebble game. Rather than having one very long run, we will now consider many runs, and each of the runs would start at site 8 in the upper right corner of the grid. Now this program contains an additional loop over the runs, and we have a total of n runs in the program. The program finally outputs the final position of the pebble at time t max. Output for t max equals 4 is shown here. Let us now represent the output using two-dimensional histograms, first for the case t max equals 0. For this time, all the runs are still on site 8, and there are no pebbles on other sites. As all the pebbles are on site 8, their proportion on site 8 is equal to 1, here represented in white. All the other sites are shown in black, as they do not appear in the output of the program. At tmax equals to 1, that is after one iteration, the output of our program looks as follows. And the corresponding histogram is shown here. At this time, about half of the pebbles is still on site 8, while there is about a quarter of the pebbles on site 5 and site 7 each. The other sites are still black because they cannot be reached within one move. At tmax equal to 2, we have the following histogram. We see that now some pebbles also reach the sites 2, 4, and 6. For larger times, we see how the pebble diffuses over the entire 3x3 pebble game, and the color becomes more and more uniform. Please take a moment to make sure that you understand the color code in this figure and test your understanding in the following little quiz. We consider the program with n runs equal to 100. As is indicated by the color bar on the right of the diagram, the color of side 0 represents the number 0.09, which is output of the program. Question 1. What is the meaning of this number 0.09? The correct answer is answer 2. The histogram simply analyzes the output of a simulation with n run equal to 100. Question 2. On starting side 8, the probability falls from 1 at t equal to 0 to 1/2 at t equal to 1 and is always larger than the probabilities at any other side. Is this always true, even if we choose another starting side at t equal to 0? It is false, as can be seen from the case of a pebble game starting at side 4, the center. The probability to be found at the starting point at t equal to 1 is 0 in this case. Question 3. Would our results change if instead of playing 100,000 consecutive pebble games, we would let 100,000 pebbles move across the grid at the same time? The results would not change at all. The probabilities represented by the color code in the figure can be correctly interpreted as the normed density of an ensemble of a large number of pebbles moving across the sides without interactions between them. Next in this tutorial 1, Alberto will discuss the simulation using a compact analytic method, the transfer matrix. It will give us the exact value of the probabilities that we just discussed. Before moving on, take your time to download, run and modify the programs. On the Coursera website, you will find the program pebblemultirun.py and also the program that allows you to generate the histogram at time tmax. There's also a program which generates all the histograms at times t equal to 0, t equal to 1, and so on in one run.
As indicated by Michael, we now discuss the transfer matrix method, which allows to solve exactly the Monte Carlo dynamics of the 3x3 pebble games. For larger systems, this method does not apply, but its lessons remain valid. If we start at the right upper corner at t equals 0, we know that the probability to find the pebble at site 8 is 1. At time t equals 1, we know that with probability 1/4 we will be at the site 5 or 7, and with probability 1/2 at the site 8. To compute the exact probabilities at all time steps, we need to introduce a vector, pi t, which contains the probabilities to find the pebble at time t at the site 0, 1, 2, and so on. As explained by Werner in lecture 1, the Monte Carlo algorithm is nothing but a matrix, the transfer matrix of transition probabilities P, A to B for moving from the site A to the site B. In the 3x3 pebble game, this matrix is 9x9 because there are 9 configurations. Let's fill in this matrix. The probability to go from the site 0 to 0 is 1/2. The probability to go from 0 to 1 is 1/4. The probability to go from 1 to 2 is 1/4. So let's fill in the entire matrix. Note the factor 1/4 in front of the matrix. It is now crucial to realize that the probability vector at time t plus 1 is the product between the transfer matrix and the probability vector at time t. In Python, this gives the following program. where thanks to NumPy we can write in one line the matrix vector product. The output is the probability vector at time 0, 1, 2, and so on, and is shown here. This is the entire Monte Carlo dynamics for an infinite number of pebble game, and it is exact. For example, the probability to be on the side 0 is 0 at time 0, 1, 2, and 3, and is 6 over 256, which means 0.023, at time 4, as you proved earlier. We also see that the equilibrium value 19, which is 0.111, is reached very fast for all sites in the system. At small time, the matrix vector multiplication modifies the probability vectors, while at longer times, this multiplication does not change the vector. Does this ring a bell with you? It means that the equilibrium probability vector is an eigenvector of the transfer matrix with eigenvalue 1. Eigenvalues and eigenvector can be computed in one line in Python, and this is the modified program transfer.py and the 9 eigenvalues of the transfer matrix. We see that 1 is the largest eigenvalue. The second largest eigenvalue is 0.75. Then we have 0.5 and minus 0.5. We have already understood the role of the eigenvalue 1 is associated to the equilibrium eigenvector. Now we will study what the other eigenvalues, and in particular 0.75, are good for. To do so, we consider again the output of transfer.py. Here we find the probability to reach any site starting from the upper right corner. Let us now subtract the equilibrium value, 0.1111, and take the absolute value. This is done in pebble transfer sub.py, and this is the output. Let us now plot the output for the side 0 in the semilog scale. The straight line indicates an exponential convergence to equilibrium, as announced at the beginning of the tutorial. The slope of this line is the same as the function 0.75 power 3, the second eigenvalue power t. Let us now put 0.75 into an exponential. This gives exponential minus t log 0.75, which can also be written as exponential of minus t over tau. Tau, which is more or less 3.4, is the correlation time introduced by Werner at the beginning of the tutorial. Let's go back to the original evolution of the probability vector pi t. It is after few correlation times tau, let's say 4 or 5, that the equilibrium is reached, and the correction to the equilibrium disappears for all intents and purposes. To understand our observations, we remark that the initial probability vector can be decomposed on the eigenvectors of the transfer matrix. The component associated with the eigenvalue 1 is conserved in time because 1 power t is equal to 1. The other components associated with the other eigenvalues lambda decay exponentially, and the slowest decay is given by the second largest eigenvalue. Before moving on to Vivien's part about rigorous solution, let's take a moment to download, run, and modify the programs that we have discussed in this section. On the Coursera website, you will find pebbletransfer.py, which contain the construction of the transfer matrix and the matrix vector multiplication using NumPy. The eigenvalues of the transfer matrix are computed in transfer pebble eigen.py. The graphics and the subtraction of the equilibrium value 1 over 9 is contained in the program transfer pebble sub.py.
Alberto has indicated that the evolution of the Monte Carlo dynamics is determined by the decomposition of the probability vector at initial time onto the eigenvectors of the transfer matrix. All eigenvalues have a modulus less than or equal to 1. An eigenvalue larger than 1 would lead to an explosion of the probability at large time. At large times, the dynamics converges to the eigenvector with the largest eigenvalue equal to 1. This is what we will call the probability vector of the equilibrium state or the steady state. When does this picture really apply? What are the rigorous mathematical conditions ensuring that one converges at large time to a unique steady state? This is what we will find out in the final part of this tutorial. There is a simple physical example in which a strange phenomenon occurs. Consider a system in which you have two copies of the 3x3 pebble game, one in red and one in blue. In each of those games, the pebble jumps from side to side with the same rules as we have seen before. If it is started in the red one, it will remain there forever, and if it is started in the blue one, the same thing will happen. The combined system is described by an 18 by 18 transfer matrix because we now have 18 sides. There are a lot of zeros in this matrix, indicating that the pebble cannot jump from the red game to the blue game and vice versa. In fact, we are in an annoying and physically unacceptable situation where the outcome of the simulation depends on the starting configuration, even at infinite times. We are also in a mathematically annoying situation because the transfer matrix of our dual pebble game has two eigenvalues 1. This is described in the program pebble dual eigen.py. Mathematicians describe this situation that we must avoid as stemming from the reducibility of the transfer matrix of our dual game. Reducible means that we can split apart the transfer matrix of our system into two subsystems without affecting the rest. One of the two mathematically rigorous conditions for a Monte Carlo Markov chain algorithm is that this pulling apart is not possible, that it be irreducible. We can in fact render our dual pebble game reducible by adding a small probability of transition between the two games as depicted here. We now observe that the pebble can change its game. This small probability can also be observed in the transfer matrix in the program pebble dual eigen.py, where it allows to recover a unique eigenvector of eigenvalue 1, that is to say, a unique steady state. We realize we must have a unique eigenvector of eigenvalue 1 ensuring that the matrix is irreducible. In fact, this is not enough. We need a second condition ensuring that the probability converges to the steady state in the large time limit. We could face a situation where the second eigenvalue lambda 2, different from 1, and possibly complex, is of unit modulus. In this situation, lambda 2 to the power t does not converge to 0 as t increases. This means that the probability vector oscillates and never converges at infinite times. To illustrate this behavior in a simple example, consider the following 2x1 pebble game and adopt the following jump rule. The poor pebble is unlucky. Not only it has only two sides where to be, but also at each time step it must go to the other accessible position. Starting from the left at time 0, it has to go to the right at time 1, to the left at time 2, and so on in a deterministic way. The transfer matrix of this dynamics is simple to write. The ones in the matrix indicate that the particle jumps to its neighboring site at each time step, and the zeros indicate that it cannot stay in the same position. The eigenvectors and eigenvalues take a simple form. The steady state is uniform, and the other eigenvector has eigenvalue -1. This explains why the probability vector does not converge in the infinite time limit. How is this phenomenon general? Let us remark that every 2 time steps, the pebble comes back to its original state. From a general point of view, we now arrive at the second of the 2 mathematical conditions that we require for our Monte Carlo Markov chain algorithm. We must avoid recurring states, situations where, when starting from one state, we are sure to find it back after a fixed number of time steps. In our 2x1 pebble game, we have 2 recurring states, which we are sure to find back after 2 time steps. They correspond to starting either from the right or from the left state. Fortunately, recurring states can be easily avoided. In our example, imagine that we allow the pebble to stay in the same configuration with a small probability epsilon. Every now and then, the pebble will stop and stay in its position. In the program pebble recurrent eigen.py, you will see how, with a small finite epsilon, the steady state becomes the unique eigenvector of unit modulus. What we have seen here has been cast by mathematicians into 2 conditions that we must supplement to the global or detail balance condition that Werner discussed during the lecture. The Markov chain must satisfy global balance and condition 1, it is irreducible, and condition 2, it is aperiodic. That is, there are no recurring states. Those are, in total, the only 3 conditions that we require the Markov chain algorithm to verify for it to behave in a proper way. Please take a moment to download, modify, and run the programs that we have discussed in this session. On the Coursera website, you will find the two following programs: Pebble Dual Eigen.py and Pebble Dual Movie.py. In these two programs, you can add a small probability epsilon for the pebble to jump from the red game to the blue game. You will see how this allows the eigenstate of eigenvalue 1, that is to say, the steady state, to be the unique one. You will also find the associated program Pebble Recurrent Eigen.py and Pebble Recurrent Movie.py. In those two programs, you can add a small probability epsilon, allowing the pebble to stay in the same position, and you will discover by yourself how the steady state becomes unique.
In conclusion, we have seen that Markov chain Monte Carlo calculations are equivalent to transfer matrix multiplications. They converge to equilibrium after an infinite number of iterations only. But this infinite number is not a serious restriction because of the existence of a timescale set by the second largest eigenvalue of the transfer matrix. In the 3x3 pebble game, the second eigenvalue gave a timescale tau equals to 3.4. And convergence towards equilibrium was reached after a few times tau, like 15 or 20 iterations. The concept of equilibrium is far-reaching, and the interest in Monte Carlo calculations is very strong because of this existence of a timescale. It separates fast and slow things. There is considerable tragedy attached to this question of the timescale tau, because in usual Monte Carlo calculations, we have a hard time estimating tau. But this will be food for thought for another session of statistical mechanics, algorithms, and computations.